Hello, my name is Giwon Park. This is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. In this presentation, I would like to discuss my recent study on how personalization algorithms affect human category learning. These days, many web-based services provide recommendations that are fine-tuned to users' interests and preferences. The so-called personalized recommendations are not limited to online shopping or entertainment anymore. However, as the use of personalization becomes more prevalent, many concerns have been raised at the same time regarding the diversity of information that the recommendation algorithms offer. The concept of a filter bubble is a good example, which refers to algorithmically curated presentation of homogeneous content to users. A major concern about the filter bubble is that it can reinforce our current belief regardless of whether it is correct or not. A biased pool of accessible information would make revising or correcting the internal belief more difficult. What is more concerning is that online content providers allow materials that can induce implicit learning using recommendations. For example, a recent review suggested that recommendation algorithms used in a content sharing platform can guide its users to problematic content which is associated with misinformation, misconception, and stereotypes. It is true that the reviewed algorithms include different approaches other than user personalization, which calls for further investigations on the filter bubble caused by personalized recommendations. That said, many of the problematic contents discussed in the article are related to factual and conceptual learning, which makes the concern about personalization not limited to preference-based consumer behavior and related domains. Given this background, we investigated the effect of personalization on category learning. Our interest was in the impact on attention in terms of information sampling, representation of categories, and characteristics of post-learning decisions. In particular, we used a cognitive model-based approach to formalize and better understand post-learning categorization by considering similarity evaluation when information is only partially encoded. In the online experiment, we asked participants to learn 8 categories of fictional aliens with 4 items per category. The fictional aliens had 6 different features which had continuous values. The experimental design resulted in 10 conditions, and we collected 20 participants per condition. The test consisted of a learning phase of 128 trials and a post-learning categorization task of 32 trials. On each trial of the learning task, a stimulus was given with all feature information covered. Participants had to uncover them to see features of each alien by clicking on a show button in some conditions or by clicking on a gray box directly in the other conditions. After feature sampling, a category label of the alien was presented. During the post-learning categorization task, participants classified independent test items by clicking on one of the category labels. After making a decision, participants also reported their decision confidence using an 11-point Likert scale. The same set of test items were presented to all participants. To make sure that the conclusion of the experiment is not due to a specific configuration of stimuli, we prepared 2 stimulus types. One is called a ring condition because the low-dimensional representation of categories form a ring-like structure. The other one is a cluster condition in which categories are generated as a sample of multivariate normal distribution without any systematic pattern. In terms of the manipulation of learning sequences, we set 5 conditions which differ in how items are chosen and features are presented. In the control condition, items were randomly selected for each trial and participants had to reveal all features. The order of feature presentation was randomized. Next, we had 3 conditions in which a personalization algorithm controlled item selection, namely conditions PR, PP, and PA. However, these conditions presented feature information using different methods. In the PR condition, features were presented in random order. In the PP condition, feature presentation was also adapted to individual participants. In the PA condition, unlike the previous 2 conditions, participants were allowed to choose features to sample actively. Finally, in the active learning or AL condition, Participants not only sampled features actively, but also chose a category to study at the beginning of every trial. Based on this category selection, one item was randomly chosen and presented to the participant. In all non-control conditions, participants did not need to sample all 6 features. The personalization algorithm used in the PR, PP, and PA conditions was based on the study of Covington and colleagues. In this original study, they proposed a recommendation algorithm based on a deep neural network. The goal of this method was to train a neural network that compresses a user profile into a low-dimensional embedding so that its similarity with vectors representing video clips explained the watch probability. Given this trained network, the algorithm recommended videos that user is most likely to watch. We adapted this original algorithm to our task in the following way. During the learning phase, participants might or might not sample feature dimensions over trials. We defined each user's sampling profile as a vector consisting of dimension-wise sampling rates. Then, we trained a linear mapping that transforms this original sampling profile into a certain user vector so that its similarity with each item vector explains the overall probability that participants will encode features. The algorithm recommended item of the higher expected sampling rates. This modification relies on the assumption that sampling all accessible features is a sufficient condition of ideal learning. As discussed before, condition PP personalized not only items but also feature presentation. In this condition, the experiment showed features in descending order of the dimension-wise sampling rate. In other words, dimensions of the higher sampling rate were prioritized in terms of accessibility. Now, we will discuss the result in 3 different aspects. First, to understand the impact of personalization on attention, we interpreted the sampling profile. We computed the Shannon entropy of each participant's sampling profile to quantify its selectivity. The scatter plot on the left side shows the result after finishing the learning phase, and the line plot on the right side shows the result as a function of trials using a sliding window with the width of 11 trials. The plot shows that participants tend to develop selective sampling patterns under the influence of personalization. In particular, if feature presentation is also personalized or participants were allowed to sample features actively, the selectivity of sampling profiles becomes stronger. Next, we will discuss how category representations are developed by interpreting confusion matrices from the post-learning categorization task. A confusion matrix summarizes the performance of post-learning categorization by comparing true category labels and predictions provided by participants. If a learner classified all test items correctly, then the corresponding confusion matrix would look like a diagonal matrix. However, if it is not the case, the resulting confusion matrix will show some deviations from the ideal case. Therefore, the distance between the ideal confusion matrix and the one derived from actual data might suggest the degree to which the category representation was distorted. Heat maps show the condition-wise average confusion matrix. You can find the confusion matrices from the control and active learning conditions are relatively similar to a diagonal matrix compared to the 3 personalized learning conditions. We conducted planned comparisons of the representational distance between the control and other non-control conditions using the Mann-Whitney U-test. The result shows that at least one of the personalized learning conditions shows substantial representational distortions compared to the control condition. Lastly, we will take a deeper look into item-wise accuracy and confidence reported during the post-learning categorization task. To incorporate item-level differences, we first focused on the manipulation of learning sequences again. Let's see this toy example case with 5 categories. During the learning phase, to participant number 1, items from 5 categories were presented equally. However, to participant number 2, who was influenced by algorithmic curation, only categories A and B were presented frequently. Meanwhile, recall that the same set of items will be presented to all participants during the post-learning task. It means that the frequency with which each test item's true category was presented during the learning phase is different between conditions. We will call this frequency representativeness or a representativeness score. We can imagine that the representativeness score of the test items will be the same in the control condition. However, in the algorithmically curated condition, test items will be given different representativeness scores. We first explored the relationship between accuracy, confidence rating, and representativeness of test items. To help in the interpretation, smoothed mean trend lines were also added. Accuracy tends to increase as a function of representativeness scores, which would be trivial. On the contrary, confidence rating shows an interesting interaction between accuracy and representativeness. When personalized learners are making correct categorization decisions, the confidence rating tends to increase as test items are of higher representativeness. However, if personalized learners make incorrect decisions, the confidence rating tends to increase when they have never or rarely studied the true target category, which means that items are less representative. This representativeness can only explain the influence of personalization on experimental manipulations. In pursuit of a more process-based explanation, we took a model-based approach. Specifically, given the nature of the task that allows partial encoding, we were interested in how partial encoding explains the post-learning categorization performance. To this end, we fitted the Adaptive Attention Representation Model, or ARM, which is a dynamic extension of the Generalized Context Model. As in the original GCM, ARM stores experiences as independent exemplars. Also, similarity between the stored exemplars and a presented probe guides category learning and decisions. Also, like alcove and sustain, ARM reallocates attention weights every trial using an error gradient. An important improvement made in ARM is that attentional dynamics pursue cognitive economy by incorporating the principles of statistical regularization, lateral competition, and memory biases. And also, ARM constrains its attention weights and their dynamics directly using data that represent encoding processes, such as eye tracking data or sampling decisions in our case. This allows the model to consider the case in which features are only partially encoded. GCM and its extensions rely on the assumption that dimension-wise similarity between a probe and an exemplar guides categorization. If a feature was not encoded in either a probe or an exemplar, we cannot evaluate the similarity in principle. However, as an alternative strategy, we assumed that participants would presume a certain degree of base similarity when a feature was not encoded, which was parameterized as C0 here. Then, how would this parameter influence similarity evaluation? Let's say that the actual distance between a probe and an exemplar is like this. If the value of the presumed similarity parameter is low, then the distance will be exaggerated. On the contrary, if the value of the presumed similarity parameter is high, then the distance will be perceived as shorter than it actually is. We fitted a version of ARM that allows partial encoding to the data, extracted the estimates of this presumed similarity parameter, and used them as another regressor of generalized linear models. We fitted GLMs with increasing interaction complexity and report the result from the variant of the lowest Bayesian information criterion. First, this contour plot shows the model predicted accuracy as a function of representativeness and presumed similarity. You can see that if personalized learners presume high similarity for any unobserved features, their categorization decisions tend to be less accurate. When it comes to the confidence rating, interesting patterns are found in incorrect trials. In general, the contour plots confirm our interpretation that personalized learners tend to be more confident when they know less about test items, which is the case of low representativeness. Also, in conditions PP and PA, low representativeness and high presumed similarity predict the highest confidence rating. In other words, if participants actually learned almost nothing about the target category but assumes that any unobserved features will be similar to what they already know, it leads to higher confidence rating even if they are making incorrect decisions. Here is the summary of our observations. Personalized learners tend to develop selective attention to a smaller number of feature dimensions. Personalization tends to distort the latent representation of categories compared to the control condition. Personalized learning experiences tend to result in inflated confidence when learners make incorrect decisions about unknown unknowns. How people evaluate similarity given only partially encoded information might provide a mechanistic explanation of this effect. This is the end of our presentation. Thank you very much for your attention, and please feel free to contact us if you have any questions.